For this project, we focused on the design optimization of an e-bike. It is a vehicle integrated with an electric hub motor on the rear wheel that accelerates and decelerates the bike within a specific speed limit. We have set this limit to 25 miles per hour, which is a safe speed for commuting inside campus. The ultimate goal of our optimization is to maximize driving range as a result of optimization process in three different subsystems. Frame subsystem focuses on minimizing the total frame mass while maintaining structural integrity. And for the energy storage subsystem, we optimized the battery packaging to maximize energy capacity within dimensional constraints. Lastly, the drivetrain subsystem aims to minimize energy consumption per mile by selecting the most efficient motor option based on our optimization results. Let's look at the inputs and outputs for each subsystem. For the frame, based on the final design of our model, outputs would be the frame mass and packaging dimensions. For energy storage, the key outputs are battery mass and capacity. Finally, the drivetrain provides the motor mass, voltage, power demand, and energy consumption per mile. The boundary condition of our system is shown in the diagram below. And details for coupling variables among three systems are right next to it and will be described in the following slides.
The e-bike's frame subsystem is modeled off a traditional design consisting of 6 unique tubes. The design variables used to optimize the frame are the outside diameter d and thickness t for tubes 1 through 6. Our optimization parameters consist of the lengths of these tubes L, their corresponding section moments extracted from structural Fe analysis SM, and the mechanical properties of aluminum, which we've assumed a density rho to be 2,700 kilograms per cubic meter and yield strength sigma yield of 276 megapascals. Our intermediate variables are tube bending stress, cross-sectional area, and area moment of inertia for each tube. And the objective function of this subsystem is to minimize total frame mass while satisfying dimensional constraints, which we've determined from commonly available tube stock sizing and packaging requirements, all while achieving a stress below yield. When modeling the frame structure, the following assumptions were made. The frame must be able to withstand an abuse loading of 3 Gs of vertical impact, which we would attribute to driving off of a curb. We assumed a maximum rider mass of 136 kg, a 5 kg battery, and a 5 kg drivetrain. We also assumed that 60% of the rider's mass passes through the seat, 10% through the handlebars, and 30% through the pedals. Our mathematical modeling approach started with designing a CAD model of the frame. An abacus finite element model was then generated and a 3G static load applied. Section moments were then extracted from this FE model, which we then put into our MATLAB mathematical model as a parameter. MATLAB then utilizes the fmin_con function to find an optimal set of tube diameters and thicknesses for the frame tubes, all while satisfying our design constraints. These are the frame's optimized values for diameter and thickness of each tube. We found it very interesting that the optimal tube thickness was consistently set at the lower bound of 1.2 millimeters. Overall, the outcome of this optimization is very lean but feasible. A table of commercially available aluminum tube stock is included at the bottom of the slide.
Our second subsystem is the energy storage subsystem. The electrical connection arrangement and mechanical packaging designs are based on number of cells in parallel NP or series NS. Parameters shown on the right are used for evaluating constraints. The B cell parameter table simulates being provided off-the-shelf cell options with different characteristics. The design variable J is used to select the row of the B cell table, which will maximize the energy capacity of the battery in watt-hours. The intermediate variables can be split into electrical and mechanical categories. On the left is the electrical schematic where battery voltage and power are calculated. The right side figures show calculations for the dimensions of the battery based on assumed optimal cell orientation and stacking directions. Alpha case and beta case were used to adjust the mass and dimensions respectively to account for a case and wiring between cells. Most of the constraints come from the electrical characteristics of the selected motor or the packaging space within the frame as shown on the left. The mass constraint came from the frame, and the battery type was selected for rider safety. All design variables are integers.
For the mathematical modeling of the subsystem, analytical modeling was chosen to model the output capacity of the battery pack. Variables and constraints were defined from other subsystem parameters and battery cell parameters. Based on defined constraints, an objective function was derived using the design variables. Genetic algorithm optimization was performed in MATLAB to optimize the objective function. The modeling methodology section describes the assumed constraints and methodologies used to optimize the objective function. Results from 5 separate simulations with different parameter settings are arranged in the following slide. The results in the table show the optimization results from the baseline simulation, along with increasing the upper bounds of the power of the motor, the maximum mass, voltage of the motor, and the range above the voltage of the motor. The active constraints on the objective function are the maximum mass and the upper limit of voltage. Optimal mechanical orientation of the cells could be further evaluated due to the excess space in the dimensional constraints.
Subsystem 3 is the drivetrain, which is modeled to size the motor so the bike meets its performance targets in the most efficient package. We capture a set of constraints: the battery power limit, the motor torque envelope, the motor's continuous power rating, and launch acceleration. Our objective function then minimizes energy consumption and cost while still satisfying all of those limits, which sets up the core trade-off between motor size, mass, and performance. For the optimization model, we treat bike, rider, and battery mass as fixed inputs, along with the wheel radius, desired cruise speed, drivetrain efficiency, air density and drag area, rolling resistance, gravity, and the available battery power. Together, these define the total vehicle mass and the forces the motor must overcome. Our main design variable is launch acceleration. From that, we derive rolling resistance and aerodynamic drag, total tractive and launch forces, cruise mechanical power, and finally, motor torque and current, which we compare to the motor and battery constraints to check feasibility.
To model our system, we treat the e-bike as a point mass vehicle model and derive the vehicle dynamics equations from this. We select available off-the-shelf motors as our candidate motors and use their specifications as the parameters to this problem. We calculate their energy consumption per distance over two operating conditions within the vehicle dynamics, and we're optimizing the launch acceleration per each motor and ranking the motors based on their energy consumption at these optimal accelerations. Since our objective function is nonlinear, as well as our constraints being nonlinear and linear, we decided to use the MATLAB fmincon function since this algorithm can handle these constraints. The results of our optimization show that our rank 1 motor is the Grin all-axle V3 with an energy per distance of 29.63 watt-hours per mile. What we can see here is that there's a general positive correlation between the optimal acceleration and the energy per distance across the candidate motors. However, although there is a large variation across the power ratings and max torque, this didn't necessarily result in a large differentiation in the energy distance and energy per distance, with only a 1 watt-hour per mile difference across all of the outputs. We can also see that although the Grin all-axle is our rank 1 motor, it does not necessarily have the lowest optimal acceleration. To summarize, we have our design variables and outputs of each subsystem listed here, with the resulting e-bike range of 50 miles. Note that this 50 miles is an estimation based on the assumptions that each subsystem had to make about each other, and our next step is to use our linking and coupling variables at the system level optimization problem to refine this estimation. Thank you.